So radiation quantities in units, measurement of just straight radioactivity, Curie and Becquerel, radiation absorbed dose, gray or rad, 1 gray is equal to 100 rads, radiation risk or the effective dose of the type of radiation is either in rem or in sieverts, and 1 sievert equals 100 rem. Often you'll see the units for sieverts as millisieverts instead. Okay, convert from activity to dose. Using gamma ray, okay, so we want to convert from the amount of activity that we have in millicuries, if we can, to and we're gonna use a conversion table based on the kind of radiation it is. In other words, we're taking a jump from millicuries through rad to or through grays to sieverts. So this is going to like make all those adjustments for us. Okay, or these constants are going to make all these adjustments for us. So we have a formula. The absorbed dose in rad per hours is equal to the activity in millicuries times the constant for gamma ray, because we're working with gamma rays here, divided by the distance squared from the origin of the radiation. So let's see what we have here. Using gamma rays, but okay, let's see the problem. Okay, calculate the absorbed dose in rad per hour at 60 inches from a 250 millicurie cesium-137 source. Okay, so let's give that a try. Let me see if I have that table written down here somewhere. Okay, so you guys want to do it with me? So let me get to my formula. You did it already? Okay, all right, good. Okay, D equals A times tau. A times tau. Okay. Oops. Shoot. Oh, having a problem here. Do I have a copy here? There it is. Okay, now I'm back in business. D equals A times tau divided by D squared. And let's see, the absorbed dose is equal to, let's see, where are we here? What was that problem? So it doesn't rad per hour, 60 inches, 250 millicurie. So the activity is 250 millicuries, and times the gamma ray constant, which is, okay, I'm going to make a little bit of room for that. Gamma ray constant for cesium-137 is 3.3. Okay, now let's get the units. Rads, centimeters squared over hour millicuries. Okay, I'm sorry, was it 3.3? Yeah, 3.3, that's there, 3.3 over the distance squared. So we want to keep our units the same. Is distance from point centimeters. So let's see, first of all, per hour at 60 inches from a 250 millicurie source. So we have 60 inches, but we need our units to be in centimeters. Somebody want to convert from 60 inches to centimeters? 152.4. 152.4. Okay, it's 152.4. Everybody agree with that? No? Okay. What's their opinion on that? It's about 2.5, right? 120 and 30, 120, 150, a little bit more than that, right? 152 sounds right. Anybody got another number? Yeah, 150, that sounds right to me too, right? About 2.5 centimeters per inch. Okay, okay, squared. Okay, so someone do the math for me here. 250 times 3.3 divided by 152 squared. In order for me to do it, I have to, I might as well go along with you guys and do it.
Because when I divided first, and then
Okay.
times it by 250.
I'm gonna square that 152.4 first. Times, okay, squared. Okay, I'm gonna put that into memory. Clear. Okay, 250 times 3.3 divided by, call memory, 0.03. Did I miss something here? Did I miss a conversion here? Okay, 0.033. Okay, 0.033. And let's see what our units are going to be now. Okay, let me, equals 0.0, equal, oops. .033. Okay, so let's see. Microcuries, we lose microcuries. Centimeters squared, we lose them. Hours, now we're missing something here. Something's gone wrong here. This is in hours, this constant, and what was our, in rads per hour. Okay, so we're just left with rads per hour. So it's 0.003 rads per hour. We all in agreement on that? And on the units? We saw how the units worked out there? Okay, whoops. Okay, we have millicuries. Okay, times rad centimeters over hour millicuries. Millicuries cancel right out there, divided by centimeters squared. Centimeters squared cancel out. So we're left with rad hours. Okay, that looks right to me. Good.
I still forgot how we get that one. The mercury 137 to 3.3.
The 3.3 came from our table, our gamma ray constants table. That's basically an equivalence. It's actually doing two things. That's actually doing two things for us. It's applying a conversion from millicuries to rads, and it's also basically kind of a quality factor, except it's converting millicuries for that particular material to rads. It's not the quality factor. Notice this is in rems, right? It's in rads per hour, right? So we haven't gone from rads to rem to evaluate what the exposure would be for a human being, what the effect of that exposure would be for a human being. Okay, let's move on from there. Okay, here's a whole series of unit conversions for these various, matter of fact, that we have in here, inches. Nope, you have to work on, you'll have to find your own for the general conversions. Okay, but basically these give you all your conversions. And this gave you your conversions for rads and rem and so on and so forth and grays, so that you could work out if you had to convert rads per hour to, what was it for the standard international unit from rads, we would go to grays, right? Okay, human body can tolerate a certain amount of radiation. Average background dose is 300 millirems per year. Where's that come from? There's a million different sources for that, right? Cosmic radiation, there's some terrestrial sources, there's medical sources, and so on and so forth. But on the average, the background dose for us is about 300 millirem per year. Anyone want to convert that in what constant would you convert millirem into for standard international units? If we wanted to talk standard international, right? What would that be? That would be millisieverts, right? Okay, what's the conversion? Is there a conversion? Okay, let's think about this. Okay, let's see. One gray, one millisievert is 100 rem, right? So 300, what was it again? 300 millirem would be 100 rem is one sievert. Well, it's gone? Okay, good. I just reconnected to connection restored. Is that showing up there? Connection restored? It isn't. Very mysterious. And it's still gone, right? Okay, okay, good. Okay, so these conversions are important. Let me give you an example of an important conversion. You guys remembered about 20 years ago that NASA worked with an international group to put up a Mars surveyor satellite? Anybody remember what happened to that thing? Exactly. They made a mistake in a metric conversion, right? So literally, these conversions are important. For instance, that conversion from rem to millisieverts was an order of 100, right? So converting properly between these things actually is something that we really have to pay attention to. PowerPoint. Yeah, that was an expensive mistake. Okay, so mechanism of injuries. There was a football coach many years ago that was a big component of the running game. And one of his axioms was that he hated throwing passes because he said whenever you threw a pass, three things could happen and two of them were bad, right? So we have the same issue here with radiation exposure. So we have ionizing radiation. It damages a cell. What can happen? Well, one thing that can happen is the cell can repair itself. And for the most part, when radiation takes place over a long period of time at a relatively low level, we either have cells repairing themselves or dying. And in fact, if they die at a small enough rate, it's not a big deal. What can happen occasionally, especially as the dosage increases and or if it's radiation exposure over a shorter period of time, you can have more cell death, and occasionally you can have transformation. In other words, you can have genetic damage to the cell. In that case, you could have all sorts of mutagenic and cancer causing and other issues that come up as injuries of that cell. So these are basic mechanism for injury in the cell. High doses, hundreds or thousands of rem within minutes, hours, or days is radiation sickness. That's acute sickness. Low doses, 1 millirem to 100 millirem, is a negligible effect. As that increases, you go from no effect at all to significant effects. Not all organisms respond equally to radiation exposure. We know that some are more sensitive to it. We know thyroid, if you have a radioactive iodine, it concentrates in the thyroid, so on and so forth. So deterministic effects. In other words, these are effects that are a direct consequence of the short-term exposure to radiation. It occurs, it causes this effect to occur. Okay, appear within hours or days after a person receives large doses of radiation, reddening, ulceration of skin, acute radiation sickness, and death. Okay, acute effects, deterministic effects. 10 to 200 millirems, a drop in white blood cell count. 200 to 450 millirems, nausea and vomiting. 450 to 600 rem, GI and severe blood system damage. LD50, I don't know what the LD50 is for. It's probably a specific animal, but LD50 is 450 rem, 600 to 1,000 rem, severe GI damage, 5,000 rem, severe central nervous system damage, and greater to 5,000 rem, almost 100% death. Okay, stochastic effect. These are effects typically that take place over long periods of time. They don't have to occur. They're stochastic because they are based on chance. So, and there is some probability effect here. So those are typically things like cancer, development effects of fetus, genetic effects, and so on and so forth. They won't always occur. They will occur more frequently with increased dosage over time. Okay, but they don't necessarily always occur. And even low doses, they may occur with even low doses, although the probability is lower. They don't show a threshold value. They don't show a threshold effect. Most of the time when when our body's exposed to some sort of toxin, we've adapted over time to be able to control our body's reaction to most natural toxins, to excrete them, to control them, and so on and so forth. So we're exposed to very low levels. Typically, we won't see a health effect from them. We won't have a measurable effect. But at some point, if we keep upping the dosage, at some point we'll start to see health effects from a toxin. At that point, we call that the threshold point. So when ACGIH defines a threshold limit value, they're talking about the level at which you start to see health effects from an exposure of some kind. So that's a TLV, right? So if you have certain kinds of exposures like stochastic effects, they don't exhibit a threshold effect. In other words, any exposure increases your risk, right? So no threshold dose for radiation-induced cancer. Similarly, asbestos has no threshold effect. There is no level that doesn't increase your risk for cancer. Very little exposure means you have a much lower risk, but you're never at the point where it's zero risk. So here's an example of a threshold effect. And if you look in this chart at the bottom here, the reason why you have this bubble and these strange lines at the bottom of the chart, which they don't bother to, it's a poor chart, they don't really bother to explain this. Let me see if I can't get a better view of this. I'm not sure that helped. Okay, look on the bottom there. The numbers that they have up here are from actual epidemiological data. So they're able to draw basically a kind of a regression line up here, where they can associate the amount of exposure to the probability of developing cancer. But down on the end here, they're actually estimating it by extrapolation. You guys remember when you took regression in biostatistics? Remember we told you that you should only assume that the data from a regression is valid in the range within which you have data. In other words, just because that line can extend down lower or can extend up higher past where you have data, that doesn't mean that effect is valid at those levels. So down here, they're really guessing at this, but they pretty much agree that there's always some kind of risk from exposure at that level. Okay, so the real takeaway here is that there's no threshold dose. The short-term effects There is a threshold effect, where you start to see below a level at which you don't see health effects, and then you start to see more and more dramatic health effects, deterministic. But as far as cancer and other kinds of effects, those are typically longer term, and there's no threshold for those. Okay. Monitoring instruments. Film badges, thermoluminescent detectors, pocket dosimeters, ionization chambers, scintillators. One of you was using, I think you were using, you were using badges. Were those film badges, or what kind of badges were they? What, can we wear them for a month or something, send them in somewhere? A quarter, okay. So one of the ways you can do this is that film badges actually have, how many of you guys have ever actually seen black and white negative film? Okay, not too many of you anymore, right? So black and white negative film has a silver salt on it, right? So I forget exactly what, it's not silver chloride anymore, it's some other silver salt, but it has a silver salt on it. When it's exposed to light, it darkens. You can get an effects where it actually gets darker. So early photographer used these plates with silver salts on them, and they were exposed to light. Then they'd be developed, and you would see light and dark spots on a plate, which turn into a picture, of course. Well, in this case, they have material that the silver salts, when they are struck with energy that produces photons, those areas that film badge are exposed, and they darken. Most film badges have two different areas. They have an area where they only have like a paper covering, and another area where they have either aluminum or a lead band across it. And the idea there is that they can distinguish between exposure to beta and gamma radiation based on the relative darkening of that film badge, on depending on whether the exposed area was just under paper, or whether it was under whether it was also darkened in the area that was protected by the aluminum or the lead. Okay, so you have film badges. Thermoluminescent detectors, very similar, except they have a material. We talked about the fact that some materials would produce photons, would glow, produce light when they're exposed to certain kinds of radiation. These kind of devices actually produce that kind, will have an element that produces light that either exposes a material or has a measuring device in them that detects the presence of light. Pocket dosimeters. Pocket dosimeters usually look like tubes. I don't know if I have one here. Pocket dosimeter looks is tube-like, and within this tube there is a fiber that's impregnated with a crystalline material. That crystal, when it's charged, expands. As it expands, you can when you calibrate it, when you first set it up, you put it into a charging device, and you look through it, and when you look through it, you see a scale kind of like this. Let me see if I can't make that bigger. That's what the scale looks like. And what you do is, as you charge it, you bring that line back down to the zero. Okay. And what happens is that as it's exposed, as this crystalline material, which is misshapen now, as it's exposed to radiation, and electrons are knocked off of this material, it returns to its original shape. And there is basically a mechanical device, a contactor that's in here that actually moves this dial over as this thing contracts again, as this this crystalline fiber contracts again. And you can literally periodically look at this thing, and you hold this thing up and see what your exposure has been. Okay, and I don't know if that milliröntgen is what milliröntgen is presumably what it's measuring. Okay, so anybody ever seen one of these things in use? I think in nuclear power plants, you're supposed to check these things every 30 minutes or something like that if you're in an area where you might have an exposure, so that you can react. The good thing about this is you can react to exposure. You just find out the bad news 30 days, 90 days after your exposure, right, with the film badge, right? So they have their advantages. Okay, so ionization chambers, similar to a Geiger counter. These have an inert gas that has that can be ionized. They set it up in a circuit. They ionize the gas, and if there's radiation present, it affects the ionization of this gas, and they actually measure the changes in the conductivity of the gas to determine if there's radiation present. Scintillation counters. Scintillation counters have a similar effect. They have a thin aluminum window on the front of them, and they have a material in them, a crystal, that when it's struck by high energy radiation, kind of like a cathode ray tube, except the opposite. Instead of beaming electrons at it to get it to glow, this releases a photon when it's exposed to gamma or beta radiation. That photon then is multiplied in a cascade that's inside the scintillation tube, so that a small amount of photons produced results in a large number of photons at the end of this tube that can be measured in terms of the intensity of light that's generated. The intensity of light is related to the amount of exposure that it's had. Amount of radiation exposure that you've had. Okay, has to be calibrated. A lot of these instruments need to be calibrated in labs before you can use them. Surface contamination. One of the ways that we're concerned, one of the things we're concerned about when there's a exposure or a spill or a release of radiation is that this material might be particulate, or it may attach itself to particulate material like radon daughters, being material that may attach itself to dust and wind up on a surface or something like that. So a common way of measuring the presence of contamination from radioactive sources is to do wipe tests, very similar to the way you do lead tests, except they would then be examined in a scintillation counter or some other device to determine how much radioactive material is present. Okay, so different kinds of material. Now, these charts, different kinds of surfaces, since the measuring that kind of exposure is important, the NRC has an extensive research on when these wipes are taken, how you can use these wipes to, number one, diagnose when you have a contamination, and number two, how you can evaluate whether the surface is sufficiently clean or not. And among other things, they evaluate like what kind of material you would use to clean it up, dry cleanup, water, methanol, special materials designed for this, solutions designed for cleanup, Decon 90, and so on and so forth. So they examine the effectiveness of these different kind of cleanup techniques in different materials, concretes down here, linoleum, aluminum, stainless steel, tile, and so on and so forth. And in the top chart here, you can see how effective that these various cleanups have been based on the type of surfaces that you've attempted to clean. Okay, basic safety factors. Some of the formulas that we've already looked at, some of the equations that we've gone through illustrate that there are three basic ways to protect yourself from radiation. I would put the first one at distance, because we know that as you double the distance, you quarter the amount of radiation that you're exposed to. Time, limiting time that you have an exposure, and the use of shielding. Use of shielding is problematic because sometimes you need a lot of shielding in order to protect yourself. Time, less time you spend near a radiation source, the less that your exposure will be. Work quickly, efficiently, rotate team. When we had the tsunami in Japan, one of the things that they had to do was the exposure levels were so high that workers in the plant that were working on containing the releases and cleaning up could only work short periods of time before they had to be replaced by other workers. Okay, sometimes down to an hour or a half hour before they had to stop working. Distance, the more distance you have from radiation dose, the less your dose will be. And again, factor of 2 is double the distance, a quarter of the amount of radiation, triple the distance, a ninth the amount of radiation. Inverse square law, similar noise, it's exactly the same formula. Radiation at distance 2, final distance is equal to radiation at distance 1 over times the square of the ratio of the two distances. I think we got to form that. That's an example, sure. There we go. Okay, let's do that one. Radiation source is 50 millirems per hour at a distance of 3 feet. At what distance will the exposure reach 5 millirems? Okay, so oh, I got that one. I2 is equal to I1 times D1 over D2 squared. Okay, so I2. Okay, so what do we know here? We know that the initial radiation source is 5 millirem. And okay, radiation is 50 milligrams. Oh, it's 50 milligrams per hour, 50 at a distance of 3 feet. And we want the final exposure to be 5 milligrams. 50 milligrams, 5 milligrams. And the initial distance is 3 feet. And the final distance is what we want to know. Okay, so do I got all in, did I have them all straight there? Initial distance, final distance. Yep, I got that right. Okay, let's figure this out. So let's see. So 3 over, so feet squared is going to cancel with feet squared. So we're going to feet squared. 5, 9 feet squared over d squared is equal to 1.1. Okay, so 0.9 is equal to d squared. So what's d equal to? Square root of 0.9. Anybody have that quickly? Where's my calculator? 0.95. Square root of 0.9. Yeah, it's pretty close to the same thing, right? Oops. 0.9 times square root. Yep, 0.95. And what are the units? What is that? Did you get, somebody said it was 9 feet? Okay, hang on a second. Let me try and get this so that it's working. Okay, let's see. Okay, so 9 feet squared, so it's 3 feet we started at, right? Okay, so that's 9 feet squared is equal to 5 over 50 is 0.1.
Right, Professor, isn't it the D1 over D2 squared, not just D1?
D1 over D2 squared, so D1 was 3 feet, right? Right. D1 is 3 feet, squared is 9. Oh, I'm sorry. Oh, my goodness. Wait a second. No, yeah, you're right. Yeah, can't do that. Okay. So D1 over D2 squared is equal to 0.9, 0.1, right? Square both sides, 0.1. If I take square root of both sides, then I have D1 over D2 is equal to the square root of 0.1. You guys encouraging me or not encouraging me on this? No? You're not happy with this?
We did the first one already? What about the 64?
Hang on a second here. So what's that? Oh, okay. I'm writing on the wrong problem. Okay. Yeah, you know what it is? I can't, there's no way for me, there's no shortcut or key that I can use to switch between. Let me just clear this. Let me erase all this stuff. There's no way for me to switch between pointer and pen without going over to a table on the side here. Boy, I really went off on a tangent. Here we go. Okay. Nope, that's not it. I went way ahead here. Okay, let's see if I can do this now. Okay, so I2 is, let's see, the final radiation level we want is 5 millirem, right? Per hour is equal to 50 millirem per hour. Okay, times D1, which is 3 feet. Am I right about that? Okay, over D2 squared. Okay, so now if I move this over to the other side, it's 0.1 and it's unitless, right? The units are gone, is equal to 3 over D2 squared. Square both sides. What's 0.1 squared? Somebody tell me. 0.01. Yeah, of course. 0.01 times. I'm sorry, take square root of 0.1. What's the square root of 0.1? What number multiplied by itself will give you 0.1? 0.32. Good. Okay, 0.32. I'm dependent on you guys because I can't switch back and forth. I got to hit 9 keys in order to get to. Okay, is equal to 3 over D2, right? Okay, so 0.32 times D2 is equal to 3 divided by 0.32. So D2 is equal to, it's going to be a little less than 10, right? 9.5 feet. Okay, now that makes sense, right? Because we move back from 3 feet to 9.5 feet, and we've reduced the exposure from 50 millirem to 5 millirem. That sounds right, doesn't it? Okay, if we double the distance to 6 feet, right, it's going to be 1/4. If we double that distance to 12 feet, it's going to be an eighth. Right, so this is kind of in between, so it's going to be 9.5 feet. And the units, the only thing that's left is feet. Okay, all right. I want you guys to agree. I need some feedback here. Do you guys agree with me on this? You're comfortable with this? Okay, good. All right, good. Because we're going to have examples just like this on an exam at some point. So let me go switch back to a pointer now so I can get back to this. And every time I touch something, it changes. Okay. It was 9.5 feet. 9.5 feet.
Yeah.
It was we rounded off. Yeah. On it. Have you guys has any of your instructors had the significant digits talk with you? I did. Okay, at least somebody did. Okay. So you really should, it's kind of hard to apply to these silly problems because we just threw a number at you 3 feet. We didn't tell you 3.01 feet. We didn't tell you accurately that 3 feet was measured. So, I mean, if you just took it at face value, that would be only one significant digit, right? But that doesn't make any sense. You know that it's going to be more than that because realistically, you can measure feet more accurately than that. So in the absence of that, I would probably, in a problem like that, consider using 2 or 3 significant digits, like 9.5, 9.54, whatever it came out to be. And the third digit wouldn't hurt. Okay, but realistically, you only know the answer as accurately as your least precise measurement. So if you only measured it roughly, in other words, oh, that looks like 3 feet. Maybe it's 4, maybe it's 2. Let's call it 3. That's only one significant digit in that case. But if you actually measured it out, you could argue that that the scale that you used could be good to hundredths of a foot. So you really know what the 3 significant digit. Radiation source, let's see, okay, good. Ways to reduce exposure. We also can reduce exposure by shielding, okay? A lot more difficult to reduce exposure by shielding, because sometimes for high energy radiation, gamma radiation, you need a lot of shielding. Shielding is a mixed bag also. Beta radiation, if you use the wrong kind of shielding, you can produce gamma radiation as a byproduct of the beta radiation, the electrons hitting that material, that type of material. So shielding has to be considered what kind of radiation you're expecting. It's not universal. It's got to be specific to the kind of exposure that you expect and to the how much you want to reduce the exposure. Not always practical in emergency shielding. Not always practical in an emergency. I think one of these slides had something like appropriate things for shielding or something like that, and one of them was hide behind the emergency vehicle or something like that. So, I guess when any shielding as a pinch is good shielding, I guess. Limit the amount of radioactive material in a working area to decrease the exposure and the risk of contamination. That's always true. I can't tell you how many times I've been in situations where people use more of everything that's hazardous than they really need to use. So with radioactive material, it's particularly important. I worked for a company that decided for a while, that they were going to get into testing road striping materials. That stuff they put on the street, those lines they put on the street, there's actually a technology behind that. That material has to have a certain amount of reflective material, a certain amount of rubberizers, a certain amount of adhesive materials, a certain amount of stabilizers, and so on and so forth. And the company that mixes that together to put it into that machine to paint those lines on the street in New York City, they have to take, every time they make a batch of this stuff, they have to take a sample, give it to a lab, and get it approved. So there are labs that specialize in, and this goes for almost anything that goes on in a construction site, concrete, you name it, specializes in analyzing this stuff. They decided they want to get into this. One of the tests that was necessary, I don't remember what it was used for, it might have been some sort of tracer or something like that, required a tiny, tiny amount of a radioactive material. So in order to test, how long it would take them to do the analysis, so on and so forth, they ordered a fraction of a gram of this stuff. Now, you guys, gram is like, not very much. I mean, a nickel is roughly 5 grams. A dime, I used to always say this, but like when I learned this, it was like, they had real nickels and real dimes. Now, I don't know what they're made out of now, but a dime, I think, is about 2.5 grams, right? So a fraction of a gram, tiny amount. They bought that stuff, right? So I don't know, this was 30 years ago or something like that, cost them, I don't know, $100 to get this stuff. It was expensive for a fraction of a gram of anything, right? So they bought this stuff, great. They've played around with the idea of doing this, and in the end, they decided it wasn't worth doing, so they didn't bother doing it. Sat in the lab for 10 years, right? At the end of 10 years, somebody said, look at all this stuff we have in this lab that we don't use. We got to get rid of this stuff. Now, normally what they do is you call up Safety Clean or these other licensed waste disposal places. When you have a lab, they come in and they do what's called a lab pack. They go to the lab, they go through all the materials, they look at what you got, and they say, okay, all of this stuff can go together. And they take a drum, a 55-gallon drum, they fill it with inert materials, and they put stuff in there, right? All the stuff that they can put together into that same lab pack, and that gets overpacked into a bigger container, right? And then they put other stuff needs to go in a different pack and so on, but they dispose of it all together. But now they come across this little vial of radioactive material. Oh, we can't take that. That's radioactive material. You need a special outfit to handle that stuff, right? That's a little tiny fraction of a gram. There's a speck of this stuff, right? So next thing you know, winds up costing them $3 grand to get rid of this a speck. I mean, like, you know, you'd shake your salt shaker and you wouldn't, and that'd be like 5 times as much of this material that they had. $3,000. I can't even imagine what it would cost to get rid of this stuff now. But at any rate, so keep in mind, this stuff is not only dangerous, it's expensive and it's difficult to handle, right? So, and you can, I don't have to tell you, it's a big deal if you don't handle it correctly. If you lose that XRF or if it breaks open, right, that's a big deal. Exactly. That's a big problem. Exactly. So anytime you have to, first of all, number one, if you don't need to deal with it, don't deal with it, except on the CIH exam, right? Hopefully your only involvement with this stuff will be on the CIH exam. If you do need to deal with it, it's important. Quantity is really important. You don't want to have a lot of this stuff around. Shielding, you know, and distance is good. Shielding is kind of a mixed bag. So radiation shielding. In this case, you have maybe there's an alpha emitter you're working with. They're just protecting. They're using plexiglass shielding in that case. On the right side, they have concrete blocks or lead blocks or something like that. That may be for gamma radiation, for X-rays, and so on and so forth. That might be inside of a wall or something like that. It might be temporary. Okay, so how can you evaluate how much shielding that you need? So we have tables for that. So here are various materials. And again, because each one of these different materials is emitting a different kind of radiation, alpha particles, beta particles, gamma particles, neutrons. Each one of them has a unique energy pattern for the material that they're emitting. It's really hard to just generalize this stuff. So literally you have to look at each individual material and go to tables or research on which that'll help you determine what you need in order to shield or deal with this stuff. So cobalt-60, in order to cut in half the amount of radiation that you're going to receive from this material, you need 1.2 centimeters of lead or 6.2 centimeters of concrete. To eliminate 90% of the exposure, you need 4.1 inches of lead. You ever pick up lead? Lead's pretty heavy stuff, right? Okay, 4.1 inches of lead and 20.6 inches of concrete. Okay, and then when you're all done with this stuff, it's temporary. Now you got to dispose of the lead, so that's a whole nother issue. Cesium, let's take a look at some of these others. Radium, 226. You need to get down to a tenth of that. You need 23.4 centimeters of concrete. What is that in inches? That's like about 8 or 10 inches or something like that, right? 8 or 10 inches of concrete. You need like more than an inch of lead, right? So if you're working, if you're in a dentist's office, right, that wall has to have a significant amount of material in it in order to really cut down on the exposure to the dental assistant that's taking your x-rays. And they also take advantage of, they leave the room, hide behind the wall, but they're also taking advantage of distance also. Okay, if they're smart, they'll go out and have lunch at the same time.
What about you who's inside the room?
Well, we're going to talk about the exposure. I think I have a slide in here that talks about the exposures from dental x-rays. They're not that great. Okay, actually, compared to other kinds of x-rays, like CAT scans and stuff like that, the exposure from dental x-rays is pretty minor, right? Because it's a really pretty local thing, right? Okay, so half value radiation said the range of penetration X-rays and gamma rays is expressed in half value layer. This is the thickness needed to reduce the incident radiation by 1/2. Oh, this is going to be a fun formula to work with. I can see that right away. We're going to have to use logarithms, I think, on this. Okay, let's do this one. What number is this on your chart? What? So that's number, I think that's the last one, right? Okay, yeah, let's do this one. This one looks like fun. Let me change color here. And I don't want green. Let's do blue. Okay, so the desired emission rate, okay, and I1 is the observed emission rate. Okay, so what did we say we wanted? I didn't get to the problem yet, did I? I got it here. What thickness in centimeters of lead would reduce 5 rads per hour of cobalt-60 source to 1 rad per hour? Okay, so we want to go from the initial emission rate, which is 5 rad per hour. Whoops. Again, I didn't change it to the pen. which is 5 rad per hour, to 1 rad per hour. Okay, I'm going to write the dimensions down here, because whenever you do any of this stuff, it's always nice to check the dimensions, because that will be a key that you messed up somewhere if the dimensions don't work out. Times 2 to the thickness of the shielding in centimeters. So that's what we're interested in, right? X over the half value layer for a value for 2 to the X. Okay, 2 to the half value layer. Okay, let's go back here and see the half value layer. Half value layer for cobalt 60 is, and we're just working with concrete. Is that what the problem said? Lead, okay. Lead half value layer is 1.2 centimeters.
1.24?
Is that what it said? 1.2. I see 1.2 there. Right? Over.
Looking at this table.
What's that? Is there another table next after this? Did I give you more than one table? Oh yeah, look at no, oh cobalt 60. Look at yeah. Okay, so that's nice. I have 2 tables with 2 different values for the same thing. Let's use this value over here because it's simpler. 1.2. 1.2. Let's use 1.2. I'll throw one of those out. I'll eliminate one of those tables, or maybe I'll try and figure out which one is right. Okay. 1.2, and what were the dimensions? I remember what the dimensions were. I think that was centimeters, right?
Centimeters.
Yeah, that's centimeters. Okay. Okay, so now what do we wind up with? We wind up with 1 is equal to 5 rad over 2 to the X over 1.2. Okay, so if I cross multiply, I wind up with 5 is equal to 2 to the X over X over 1.2. I'll go back and look at the dimensions later on. So how am I going to solve that? Well, it's an exponent, so probably the easiest way to deal with this is to convert both sides to logarithm. So I have log 5 is equal to, well, how do we deal with an exponent when we have logarithm? We just move that down and multiply it by the log of 2, right? It's X over 1.2 times the logarithm of 2. Okay, so now we have to look up the logarithm of 2. So can someone do that on their calculator, or shall I do this here? I'm going to need you to, if I'm doing here, I'm going to need you to write this down for me. Okay, so the logarithm of 5, yeah, let's see, I'm going to get it. Okay, clear. 5, the logarithm of 5 is 0.698. Let's call it 0.70. Logarithm of 5 is 0.70, and now I need the logarithm of 2. Okay, good, thanks. Okay, let me go back to this. Okay, so the logarithm of 5 is 0.70. I have to find a better way to do this. This is just too frustrating. So this is 0.70 is equal to X over 1.2 times 0.3. Okay, 1.2 times 0.3. Okay, divide by 0.3. Okay, multiply by 1.2. And I have what X is equal to. 1.2 times 0.7 divided by 0.3. Can someone do that for me? 1.2 times 0.7 divided by 0.3, 2.8. So we need 2.8 centimeters of lead to cut that exposure in half. Now let's just take a look at what our dimensions were. So this is 5 rad per hour. And this is rad per hour. And this is I don't think I think it's dimensionless. This is centimeters, and I think this is dimensionless. The half value is, oh, it's centimeters. Okay, so that winds up, rads per hour, and winds up just being equal to centimeters. It's 2.8 centimeters. Does that make sense now? So what was the problem again? We want to go from 5 rad to 1 rad. So if we, let's just analyze that in our heads to see if that makes sense. Let me first erase all this junk that's on here so we can look at it rationally. I'm going to go back to this table. Okay, and here, let's see, we got 1.2 centimeters of lead to cut down the amount of radiation in half. So if we put 1.2 centimeters of lead, then we have, now imagine this, each one, I'm going to take 1.2 centimeters of lead. I'm going to put it in the way. Then I'm going to take another 1.2 centimeters, put it in the way. So the first time I do that, it cuts it in half from 5 to 2.5. Now I take another 1.2 centimeters. What does that do? It takes the 2.5 and cuts that in half to 1.25. Right. So now I'm at 1.25 after I put up 2.4 centimeters of lead. So we're almost at the point where we are at the 1 rad per hour that we are interested in getting to, and it took 2.4. So our answer of 2.5 or whatever it was sounds reasonable. Okay, so you're on the CIH exam and you have multiple choice, and the multiple choice is 2.5 centimeters, 5 centimeters, 11 centimeters, or 1 centimeter. What's the right answer? Huh? 2.5. Right. You didn't even have to use the formula. You read the chart, use your judgment, and figure it out from your judgment. You'll see a lot of questions like that where you can solve them by doing a lengthy calculation, or you can make a reasonable estimation and then choose the only answer that's reasonable based on what you can see from the chart. But just remember that what you're doing is each time you go through that amount of material, you're cutting it in half, right? So it's not just like putting 2.5 and saying, oh, that's 4. I just doubled that, so that changes it to 2.5, from 5 to 2.5. Okay, so in any case, hopefully that will help a little bit. Okay, this half value labor, 5 shielding materials, lead, copper. Oh, I see. Okay, so on this one, we just said lead. We had lead and concrete on this one. This gives you some extra materials to work with. And what do we say? 1.2. It's not that different. 1.2 versus 1.24. If you were rounding down 1.24, what would you round it down to? 1.2. So the tables are the same, basically. This one, it just gives you an extra digit. Okay, let's see. Good. Okay, employee, how are we doing on time? Okay, good. External, now the other issue is that you can have 2 different kinds of exposure. You can have external exposure, internal exposure. With some materials, whether the type of exposure is not going, it's going to go through you anyway, so it's not going to matter that it's external. And others like alpha radiation, the enormous difference between external and internal exposure. So internal hazards can be the result of like ingestion, inhaling the material, so on and so forth. Internal hazards, if you have in a situation where there's dust or an exposure that could create an internal hazard, you want to use personal protective equipment, and you want to establish protocols for how you're going to protect workers from that material. Worker movements should be, and if you have an exposure, you want to restrict worker movements. You don't want them moving through an area that's contaminated. You want to isolate and clean up. If it's a spill or a release, you want to clean it up as quickly as possible. Before you do that, you want to evacuate the area. Make sure you have a proper protocol for protecting workers that are going to do the cleanup. And you're going to be required to measure the worker's exposure using various kinds of monitors, the various kinds of monitors we were talking about before. So who regulates all this stuff? Who decides what the rules are for this stuff? Well, we're going to take a look at that right now. Date modified. Okay. 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 Control programs. Radiation health and safety program should establish the following procedures. Radiation exposure monitoring. You are in a program that you're monitored for radiation exposure. Decontamination and disposal, and record keeping. Do you have a procedure that you use if there's a problem with the machine?
Yeah, we have an emergency protocol procedure. It just involves setting up the perimeter, using the Geiger counter to assess the levels, and then depending on how bad it is, you either contact local authorities or, God forbid, if you crack open the source, you have to contact the nuclear
Regulatory agency. Well, okay, Nuclear Regulatory Council. Okay, good. Yeah, because they're the ones that monitor medical equipment and this kind of stuff. Okay, and establish them. You just mentioned establish a control area, contain the area, and determine how bad it is. So you have a written emergency procedure or for dealing with if this device has a release. So among the various kinds of control programs that we have, of course, you have engineering controls, can be containing the material, can be shielding, can be, and in terms of security, interlocks, tamper-proof screws. Your instrument, you can't open the window unless it's pressed against something, right? It's got an interlock switch on it. Okay. Oh, yeah. So it's a password. You have to enter a password, and you also have a physical interlock where it's got to be pressed against the surface before you can actually open it and expose it. Can you bypass? I think in the X-ray ones, the ones with the tubes, I think you can actually turn that off.
You may be able to.
Yeah.
I didn't.
Okay. I have a suspect on yours you can't.
Yeah.
Right.
I wouldn't want.
I think in the X-ray tube, I think you can. Security seals. Access controls, key cards, facial recognition, all that kind of stuff, right? So you want to limit access to all these materials. Administrative controls. You have a procedure, that's written procedure. Formal authorizations. Here's a form for who's authorized to go into this space, what activities they can do in this space, what materials they can handle, labels, signs, postings. You've all seen these signs in medical facilities for sure. Okay, ways to reduce internal exposure. Same as the other stuff, but you want to avoid ingestion, inhalation, or absorption of these materials. And of course, with injection and inhalation, that might involve limiting material getting into the air. Ingestion might involve hand washing procedures and so on and so forth. Yeah, as a matter of fact, here, protective clothing such as lab coats, gloves, and safety glasses. Self-monitoring reduces the spread of radioactive contamination. Surface contamination, you want to avoid transfer materials to surfaces and then from surfaces to other workers. Contamination can be located with a DRI, direct reading instrument. I guess that means. Anybody have a better guess at what the DRI is? I think it means direct reading instrument, like a Geiger counter. Okay. Use a clean piece of filter paper to wipe surface and test, right? And as we were talking about before, that wipe tests are very frequently used to monitor the levels in dust and on surfaces and so on, and whether the adequacy of cleaning up after releases of material. Surface contamination, risk of transfer from radioactive material to a worker, from worker to worker, and so on. Contamination can be located again with DRI, direct reading instrument, I think. Use clean piece of filter paper to wipe the surface and to test. Okay, upon completion of work, hand washing is good work practice, important final step after working with any radioactive material, as is normal practices with a hazardous material. No smoking, no eating, and so on and so forth in the work area. Occupational standards for ionizing radiation. Okay, now there's a series of different organizations that are involved in this. If you work in a nuclear facility, manufacturing rods, waste disposal, medical facilities that use radioactive materials, they're regulated by the Nuclear Regulatory Council. The Mine Safety and Health Administration regulates exposures associated with mining and so on. And OSHA basically regulates any others that are outside of those groups. I think the NRC is a branch of the Department of Energy. Standards, okay, and the standards are based on as low as reasonably achievable. And you can imagine that it's very difficult to establish permissible exposure limits for specific exposures because there's so much difference in the type of radiation and the quality and the health impacts that it can have, how much time it takes place over, and so on and so forth. Nuclear Regulatory Commission oversees the safe use of nuclear energy and radioactive byproducts, licenses nuclear power plants and test reactors. It also regulates devices like the XRF and the medical facilities that use radioactive materials. Okay, Nuclear Regulatory Commission missions regulate civilian use of byproduct source and special nuclear materials, reactors, commercial reactors generating electric power, research test reactors. If you have a school that has a reactor, I think Stony Brook has a reactor, right? Don't they? I think Stony Brook, maybe Columbia. Do they still have one in Columbia? Not sure. Anybody know? Are there any operating nuclear reactors in New York City? Like in educational facilities? Definitely Stony Brook has one, right? So we know there's one on Long Island. Okay. By the way, why wasn't the power plant on Long Island certified to operate? Shoreham. Anybody know why it wasn't certified to operate? What was the problem that they couldn't get the Nuclear Regulatory Commission to approve its operation? That's it, exactly. There was no problem with the design of the plant, the operation of the plant, anything else. They just couldn't, they just would never achieve the point where they would approve an escape plan for the community in general. So the idea of all of Long Island evacuating a nuclear disaster on the Long Island Expressway wasn't appealing to them. So for those of you who have been on the Long Island Expressway. So materials, they also regulate nuclear materials in medical, industrial, like your application, academic settings, and facilities that produce nuclear fuel, waste, transportation, storage, and disposal of nuclear materials. So they regulate the people that would take care of the disposal of the material I described to you in the lab. It's headed by 5 commissioners appointed by the president, and the current commissioner has been there quite a while. She's Christine Svinicki, and she was actually originally appointed as a commissioner by George W. Bush, and she still was around for the Obama administration, and Trump just promoted her to chairman. She's the chairman now of those 5 commissioners. So she's been around for quite a while. Whole body annual dose limits. So this is what the NRC considers the closest thing that we have to permissible exposure limits, or limits at which you can't work in that. You can't have any further exposure during the course of that year. Whole body exposure, 5,000 millirems per year. Extremities. Now, how much was background radiation again? Anybody remember? 300, right? So 5,000, not all that much, really, for whole body annual dose limit, right? Extremities, 50,000 millirem per year. Why is it so much higher, extremities? Well, because certain organs are more, like radiation can affect certain organs more than others, and so extremities are considered less susceptible to short and long-term effects from radiation. Skin, 50,000 millirems. Eyes, 15,000 millirems per year. Pregnant women, 5,000 millirems per term, 50 millirems per month, and the general public. And this is on top of the background exposure, 100 millirems per year. Environmental exposures. If you're a smoker, you are exposed to 1,300 millirems. I don't have a period on that. I think that may be just total exposure for 20 years. I can't see that. I can't see that being per year, but I'm gonna have to, I'll check that. But 1,300 milligrams, so cigarette smoking is a significant exposure, incorporates, in addition to all the other hazards, a significant exposure to radiation. But that's a special kind of radiation, right? It's not external, it's internal radiation. So that makes it particularly concerning. Where does it come from, that radiation? From cigarettes. It comes from minerals in the soil where the tobacco is grown, and sometimes from fertilizer that they use. Medical doses, 53 milligrams on average. A dental exam, 16 milligrams, not bad. Mammogram, 25 milligram. A TC99M, I think that's a nuclear stress test. Anybody know what a nuclear stress test is? Anybody taken a nuclear stress test? No, I guess not. Nuclear stress test, you know what a stress test is? You get on a treadmill, they monitor your EKG as you're stressing your heart, as your blood pressure goes up, and so on and so forth. They're watching the electrical activity in your heart. A nuclear stress test, they do this basically the same thing, except before you take this, before you are exercised, they intravenously apply a radioactive tracer. This radioactive tracer tends to deposit in muscles, especially muscles that are active, right? So if they inject you with this stuff and put you on a treadmill, where is this stuff going to accumulate? Some is going to accumulate in your legs, right? But a lot of it is going to accumulate in your heart. So after you're done on this exercising for 10 minutes or something like that on the treadmill, and they think that enough of this material is accumulated in your heart, you've got it in your chest. It's a lot of places and stuff like that. They want it to diminish a bit, right? And just hang around certain places a little bit in the muscles, a little bit. It'll hang around the muscles a little bit longer. It's take a little longer to be excreted or removed from your muscles. You wait for 2 hours or something like that, an hour or two or something like that, and you come back. And they put you, I don't even know what to call the machine. They put you into a machine that is the opposite of an X-ray machine. Instead of sending X-rays through your body sends X-rays to their sensors. And they map your heart to see where the radioactive material has accumulated. So if you have a coronary artery that's clogged up, that area of your heart will not be glowing as much as the other areas of your heart. So they can use that as a better measurement, a non-invasive way of measuring coronary artery disease. What's the invasive way? What's the gold standard for measuring coronary artery disease? You young people, you're terrible. You don't think about any of this stuff. It's an angiogram. The angiogram's invasive though. They have to thread find a vein in your leg and thread a catheter all the way up into your heart and then release a dye. And as they release the dye, opaque, radio opaque dye, they're x-raying your heart so they can see how quickly, when they spray the dye in, how quickly it passes through your coronary arteries or your various coronary arteries, and they move it around to check different areas. That's invasive. That's dangerous. It's not like, let me put it this way. It's a relatively safe procedure, but it's not without risk. This is a non-invasive procedure. Okay, so they can do this as a substitute for an angiogram or presumably it's considerably safer than an angiogram is. Now, what's that?
From my personal experience, that test is not very good.
It doesn't have a very good predictive value. Statistics again, right? You guys remember predictive value? In other words, they get a certain amount of false positives and they get a certain amount of false negatives. So yeah,
Because what they did a test in my line down.
Yeah.
And I passed with 5 colors, but I had a problem. So I had to do an angiogram.
Yeah, there you go. Okay. So yeah, so it isn't as predictive. The gold standard is the angiogram, right? That is, you really know what you got then. So in fact, the research that they've done, when they do tests like this, they research on how well they work, how predictable they are. In other words, how good they are. So what they do is they compare people that have had this test and been negative or positive to the results of angiograms that those people had later on, so that they could determine how good a test this was. I think the positive predictive value is not all that high with this test. I think it's like 60 to 80% or something like that. So a lot of people that are positive don't have a problem. And then the negative predictive value isn't much better. So a lot of people do have a problem this doesn't catch, right? But it's better test than the ordinary stress test. It's better at predicting coronary artery disease than just a plain old everyday stress test is. Okay, so at any rate, so that's the source. I think that's what that TC99 M refers to, 75 milligrams. What's the other issue with this stuff? Now that you're walking around, you have this radioactive material in your body. What do they tell you not to do? Tell you to stay away from pregnant women, right? And children, right? Because you're radioactive for about 2 or 3 days, right? Until you excrete this stuff, right? So cranial CT, multiple scans, 5 rem, full body CT scanning 1 to 2 rem for a CT scan, full body CT scan. You hear these advertised all the time on the TV. Oh, come in, you're getting older, you're 40, come in here, we're going to give you a full body CT scan and you'll know whether you're healthy or not, or you have any problems and so on and so forth. Well, maybe you don't have any problems going in, but afterwards, who knows? So that's 1,000 to 2,000 millirems that we're talking about. Spiral whole body CT scan, I have no idea what that is. 3 to 10 rem. Building materials, 3.6 millirem. In other words, you have exposures from various kinds of building materials, particularly granites and things like that, because sometimes granites can have some radium and some other materials in them. Did I tell you guys that we were doing some in-air quality testing at how can I tell you this without telling you who it is? It's a woman that's on TV, has a lot of, like one of these shows, and does a lot of cooking things and a lot of other things. And she hangs around with Snoop Dogg. So at any rate, we did something there. She was not involved because I'm sure she's not a hysterical person, I guess. She was not involved, but we were doing work for her company, and I'm getting unplug myself here. And we do work for her company. And while we're doing the air quality testing, somebody at that company saw us running around and said, gee, I heard that you could have radon from granite countertops. And they had the world's biggest granite countertop I ever saw in my entire life. Because you can imagine they do filming and they do testing there and stuff like that. So they said, we want to test this granite countertop for radon. How would you test a granite countertop for radon, do you think? Well, how do you test the basement for radon? Yeah, that little canister, activated charcoal packet or a canister, or you can have a track etch meter, a little device that hangs around for months. But most people use these little activated charcoal canisters. You expose them in the basement for a couple of days, and then you pick them up. Well, how about a guy on a countertop? You're going to just put it down on a countertop? No, what you do is you tent it. You put something over it, so if there's radon in it and you're generating, like a contaminant, that it's contained underneath there. So you put it in there, you cover it with presumably not something like ceramic that might have some other radioactive material, it's some plastic or something like that, and then leave it there for a few days and then have it analyzed just the way you would analyze a basement. If you're buying a new home or if you're moving out to Pennsylvania, and you want to build on a certain area, and you're concerned about radium, because that's radium prong area, and you're concerned about radium in the soil and radon and so on and so forth. One of the techniques that they use now is that to analyze because if you have a radon problem, it helps to know in advance, because then you can design your foundation and your basement so that you have drainage and ventilation around the basement, so you can keep it under a negative pressure and you can avoid having this stuff leak into the house. right? So you can keep like the area outside of the foundation under a negative pressure, so we won't get stuff from the house. You do the same thing. You just put a sensor, tent it over the soil, dig a little hole, tent a dry area, put it in there, leave it for a few days, and then have it analyzed. Yeah.
So why did you tent it with the whatever?
Yeah, because otherwise you're just measuring the air, right? In other words, one part's of it on the surface, but then it's getting out into the air.
That should be tented in the basement as well.
Yeah, no, not in the basement, on the soil. In other words, rather than in other words, we're just checking a lot before they build.
Yeah, so why don't you test it, tent it inside of the basement?
Oh, you wouldn't bother because the basement itself is a confined area, right? You close the windows. The idea is that, if you read the packet or the instructions in the packet, it tells you to close up all the windows and remove any ventilation from the basement so that you get a kind of a worst case scenario in the basement. In the kitchen, well, you wouldn't measure it. Oh, you mean in the kitchen?
Yeah, the one you meant.
Oh, yeah, that's that's a big HVAC system, right? I mean, it's an office building. You get 6 air changes an hour in that place. There's no way to, confine it. And that was our way of confining it, so that we would get a worst case reading or something like that. And no, it didn't have any rating. It didn't have anything in it. And even if it did, it's so insignificant, getting diluted by the air that who would care? Okay, so some environmental exposure. Okay, smoke detectors. Yes.
Before we go on, I found the name of that scan for the hurricane.
Oh, yeah.
That's the SPEC scan, and it's a scintillation camera, actually.
Oh, scintillation camera. Okay, there you go. Okay.
Photon emission computerized tomography.
Okay, great. Terrific. Thank you. Okay, so building materials, smoke detectors have, there are two kinds of smoke detectors, right? Photo detectors and ionization detectors. The ionization detectors have a little ionization chamber in them, a little gas chamber in them. They have a little speck of an alpha emitter, Americanus, I forget what it is, what is it? Americium. A little speck of an alpha emitter in there. And that alpha emitter hits air, I think it's just air in that chamber, hits air molecules, ionizes them, and makes that space conductive. And if you get smoke in there, it interferes with the production of those alpha particles, or those alpha particles hitting the air molecules, so the conductivity goes down. So I think that's how they sense it. Do they still sell them? I think there's a few states that have outlawed now because of the disposal issue. In other words, what do you do with an old smoke detector? You throw it in the trash, right? So I think, anybody know if they've, I don't think they're outlawed in New York, although I don't think I see them in New York very much anymore. Anybody know if they're outlawed in a couple of, I think Massachusetts, a couple of states I think have outlawed them. But at any rate, the issue was not that they were dangerous, but that they were a disposal issue. Okay, source of exposure, medical. Inhaled radon, one of the biggest sources of exposure. Again, it's the second leading cause of lung cancer in the United States, the first being smoking. Okay, radon decay. Radon, again, the process is radium is a mineral, is a solid. Radon is a gas. The gas can be pulled into a house, into a basement, because it's very frequently the negative pressure, because you have boilers operating in, you have warm air rising, so the basement's under a negative pressure. So it seeps into the basement of the house, accumulates in the basement of the house, and because of poor ventilation. And as it decays, the radon daughters, the elements that it decays into, have very short half-lives, and a lot of them are solids. They attach to dust particles in the air. You wind up in the basement, you breathe them, and you have a significant exposure. X-ray machine uses essentially a camera. It uses X-rays to expose film instead of visible light. The difference in density of materials in your body cause it to have different density. I don't think they use film anymore at all. Anybody see a doctor that still uses film? Or they use, it's all electronic now, right? Yeah. I think you might still have some old timers still using film. Okay, that's okay. X-ray machine has a kind of a picture of an X-ray machine. I think we've all seen enough of them. Other sources of radiation, cosmic radiation, in other words, stuff from the stars. Matter of fact, there is a version of cosmic radiation which is called cosmogenic radiation. Anybody know what cosmogenic radiation is? What the source of that is? It's radiation associated with the birth of the universe. Cosmogenic, right? So as opposed to cosmic radiation from many other sources in the universe. Of course, we have our atmosphere, which shields us from some of this stuff, but as you increase elevation, you are exposed to more of this natural radiation. And if you're a pilot or you work for an airline, you have a significantly increased exposure from being at 35,000 feet, so much. Radioactive material in the Earth's crust, again, granite is one of the radionuclides in the body from food or inhalation. Background radiation by evolution. Here's, for instance, here's a comparison of the amount of exposure from at sea level and at 10,000 feet, 140 milligrams versus 30 milligrams per year. Anthropogenic sources of radiation, in other words, man-made sources, consumer products, your smoking and cigarettes and your smoke detector and so on and so forth, X-rays used in medicine, radioactive substances used in industry, nuclear power generators, although God knows they don't really release that much, do they? Unless there's a problem, and they don't have problems too often. But you know, I think France generates 50% of its energy from nuclear sources. What's the big difference between power plants in France and power plants in the United States? Anybody know? Right? Power plants in the United States, almost every one of them is a unique design. Power plants in France are almost always based on the same design. When there's an upgrade or a safety issue, it's like Ford, they upgrade all of them. So most of their plants have either a similar or identical design. So functionally, they have much more experience and a much longer track record on operating them safely. But here, we design it every time you build one, you redesign it from scratch.
Are they government-owned and operated?
I don't know. I would think so, right? They're all communists anyway. All of course they're government. Of course they're government operated, right? Why else would they all be the same design? Why else would they do it practically like that? Okay, nuclear power generated. Okay, radioactive from production detonation. They're radioactive from past radioactive sources. You know, you go out to Nevada to the test areas and so on. You'll know that there are areas out there that have some natural background radiation from sources and from releases in the past. Cigarette smoking, again, depends on where it was grown and what was in the soil. OSHA has their own standards, okay, non-mining and non-medical, and it's just basically whatever you can think of that isn't already covered by NRC. OSHA standards, skin, notices in sieverts. And oh no, we got millirems also. 50 millirems, eyes, 15 rems. Almost exactly the same as the NRC measurements. Mine Safety and Health Administration, again, to regulating mines are a unique kind of environment. So, you know, that's a whole nother world. Standards. And the unit of measure, K, is calculated. Okay, and they have their own working level. They have their own system of defining it called working levels. And you know, I think radon, some of the radon kits, early radon kits used the the Mine Safety and Health Administration standards for determining an early exposure limit. So some of the kits will say that the action level is 4 picocuries per liter, which is equal to one working limit. So I think that WL, that working level, is from an old mine safety standard, because they have exposures to radon also, and they had some research on what would be reasonable action levels for exposure or limits for exposure to radon. Okay, so they were dealing with it well before people recognized it was a residential issue as well. Radiation evaluations, two types of hazards, internal, external, different types of ionizing radiation, each distinct. If you really get into this stuff, you really want to deal with a health physicist that specializes in radiation. And we'll try and figure out some review material for next week that might help us with that. And then let's start on non-ionizing radiation as well, time, distance, shielding. And of course, before we leave, we have to identify all of the creatures that are a result of radiation exposure. Okay, everybody knows what that one is, right? Godzilla. How about that one? Mothra. Good. Okay, we got somebody who knows that. How about this one? Who is that? That's Peter Parker being bitten by a radioactive spider. And you have the Hulk, of course, right? He was exposed to radioactivity. Now, special credit for that one. Giant ants. No, it's from a movie in 1955 called Them. Okay, in which ants in the Nevada, after testing in Nevada, grew to enormous size and started to devour people. But this before Vegas, so whatever town was out there before Las Vegas. Okay, guys, good night.